Now this is a boost converter, and I will show you how to control it with an intuitive MPC controller. So the MPC controller solves a optimization problem and gives out the S, which is the signal that goes into the MOSFET. Now the S could either be 1 or 0. So when it's 1, the MOSFET is on. So we can just write on here. And when it's 0, it's off. When the MOSFET is on or off, the current changes. So when it's on, the current increases. So the change of current is positive. And when it's off, the current decreases. So it's less than 0. So the idea of this MPC controller is that we calculate the next step of the current. So it's k plus 1 based on the model and the current states. Now, if we just look one step into the future, we will calculate the next current, this one, with first S equal to 1 and then S equal to 0. And then we choose S to be the one that gives the least error. So I will show you what I mean. So this is the pseudocode of the MPC. It is the function that is defined within the MPC block that I showed you earlier. So first we define the cost variable, which is the cost of the different scenarios. And then we go through all of the different S. So we have 0 and 1. And then we calculate the next IL with the state that we have in the for loop. And you also have to include VI if that is not constant here. And then we calculate the cost, which is the reference value, or which is the absolute value of the error. Actually, you have to calculate the next IREF as well. But because the sampling rate is so quick, we just assume that it's the same. And then we compare it to the optimal cost function that we have from before. Now, because the optimal cost starts at infinity at first, we know that the optimal cost will become the cost when it's off after the first iteration, because it needs to be less than infinity. But in the second iteration, if the cost of when it's on is lower than the cost of the optimal cost, aka the cost when it's off, then the optimal cost becomes the cost when it's on. The optimal state will become the state. In order to make a real code out of this pseudocode, we only need to find the function in order to find the next step of the current. So I will show you that now. So we're just going to do a basic approximation for this case. So we assume that IL of k plus 1, which is the next current, is equal to the current, so k, and then plus the sampling time multiplied by the change of current over time of the current state. So we know the current, and we also know the sampling rate. So we only need to find the change of current. And from the formula from the inductor, we know that the change of current is equal to the voltage over the current over L. When the MOSFET is on, we know that the voltage over the inductor is equal to VI. So this is equal to VI over L when it's on. So when on. And when it's off, we know that the voltage over the inductor is equal to VI minus VO. So we write down that VI minus VO, and then over L. And this is when it's off. So we see that these two functions here are pretty similar. So we can actually just multiply VO with 1 minus S. So when it's on, it will become VO multiplied by 0. And when it's off, it will become VO multiplied by 1. So we can set this to VI over L, and then minus 1 over L, and then VO multiplied by 1 minus S. So this will be the function in both cases, both when it's on and when it's off. So we can put this into this equation. So this will be the code for the MPC. And here is the equation that we just found. Now, if you try to simulate this, you will notice that the switching frequency will become really high because it will be equal to the sampling rate of the simulator. We can actually make a fixed switching frequency by adding a if function. And we also need to measure the time. So this is the code for the new MPC. So it's the real time, this is the t. And then we have the old time, which is the last time we calculated this s. And then we have the switching time, which is the period of the switching frequency that we want. So after every time we calculate the s, we set t old to t. And then we also want to preserve the the s optimum. So we just set it to s old. So every time the time is less than this, the switching frequency will not change. It will just be set to the last s. This MPC is not the best that you can make because it only looks one step into the future. But now if, for example, we make another MPC which looks several steps into the future, then it will become better. And we also do some approximations. For example, we don't have the best solution to find the next step, but this will work pretty well for just a regular boost converter where the parameters doesn't change that much. But for example, for a PFC where VI changes a lot, then it would not work that well. To make this MPC even better, without changing the steps that will look into the future, we can actually add some more variables into the cost function. So we could, for example, add this, which reduces the switching frequency. So for the cases of s, where s is equal to the last s, this will become 0. But when s old is different from s, this will become a positive term. And depending on the weight, so this term will actually increase the cost of switching, which will sometimes prevent the MOSFET from switching, even though we will come closer to the reference value.